So in our case here, we have this given beam section. And since we have it, we have all the properties. It's going to be also given with it. So you have all the information. We have the moment of inertia, we have our squared, we have cross-section area, C top, C bottom, section modulus top and bottom, and the self-weight of the beam, the dead load. The span is given to us. It says here 65 feet. This is going to be the full span. Dead load 393, like what is mentioned here. P left pump per linear foot, meaning 0.393 kip per linear foot. Here is the superimposed dead load, 0.1 kip per linear foot. Life load is going to be 1.1 kip per linear foot. All of this information is given to us. It says here the beam contains 13.5 inch ASTM 416 strands, 270 KSI. We have also non-tension steel, 4 number 6s is giving the tension side. It says here for the FPE, in this example, only use 155. So typically we use 150, but for this specific example, we're going to be using 155. Now let's see what we need to do. Number one, it says determine the cracking moment. At what point do you think the moment that this beam here is going to be cracking in terms of what moment? Second item, it says for the given loads, determine the load stage at which the beam is going to crack. For example, do you think beam is going to crack once you just support the beam in 2 supports, one at each end, just you do the self weight of it? Or once you add the superimposed dead load and you don't have the life load yet? Or is going to crack when you add the life load? Let's give you the question. So we need to know at what stage this beam is going to crack. Or it will never crack for this given loads. If all the moment due to all of this loads is going to be lower, the cracking moment means this beam is not going to crack. So you know that the design of this beam was meant to have uncracked beam. So this says here, where do you think the cracking stage or what load stage the beam is going to crack? Also, it says here, determine the overload moment beyond the cracking point. So for example, let's say this beam is going to be exposed to 100 kip foot and it's going to crack at 80. So how much is the overload moment? I'm going to say overload moment is going to be 100 minus 80. So you have additional 20, let's say kip foot, before the beam is going to be reaching the applied load. And it's going to start to crack at 80. And then it says here, what is the safety factor against cracking? So I'm going to say here's safety factor. You'd like to see a safety factor if the cracking is the issue. You'd like to see here a safety factor more than 1. So in the case, the simplified quick numbers that I give you here, when I say 100 is going to be the total moment, and 80 kip foot is going to be, let's say, the cracking moment, it means your safety factor is going to be 0.8. Because actually your beam is going to crack before it goes to the last or to the total load, total moment. If you tell me here in another example that the cracking moment, let's say, is 500 kip foot, and the total load is going to be equal to 400 kip foot, I'm going to say here the safety factor is going to be equal to 500 divided by 400. So in this case, you're going to have more room. You still have 25% out of the 400 that you can go without any cracking. We're going to see how it works here. So this here, it doesn't have phi min yet. Phi min is going to come, which is the strength is going to come in the following example. But let's first here study the cracking moment and when do you think the cracking is going to happen, after which load or what load stage, and also this overload and safety factor for the crack. So I can say, okay, I have the span, I have dead load, life load, and I have superimposed dead load. It should be a simple task here to find out moment due to dead load, moment due to superimposed dead load, moment due to life load. With this equation, W squared divided by 8. You have here simply supported beam. The span means the distance from a support to a support. It is not the width of the beam, right? This is the span. This gives you the distance from a support to a support. Now let's find here the cracking moment. In order for us to do the cracking moment, we need to know how much force that we have applied on this beam. So we have 13.5 inch strands, cross-section area total, is going to be 199 square inches, almost 2 square inches. Effective pre-stress is going to be 155 psi. We have total of 308.45 kips. This is going to be P sub E. So, okay, now this is going to be the amount of force that you put on the beam and after losses. Now let's go here to our cracking moment equation that I was just talking about at the beginning of this lecture. The cracking moment, which you'd like to see how much this is going to be, is equal to P sub E, which I just determined in the previous slide here, the amount of force that you apply, E, eccentricity, and then what do you have here? R squared divided by CB plus FR, which is 7.5 squared root of prime C, multiplied by S at the bottom, because you're looking for that point when the bottom of the beam is going to be cracking. So FR or FCR is going to be 530 psi. R squared divided by CB, all of these factors and the section properties was given in the first slide of this example. Just take you back here to look at it, all of these values. So what you can do here is to find out R squared divided by CB, take all of these values, plug into this equation here for the cracking moment, and look at the cracking moment. Turn to be 781.24 kfoot. So now, based on this simple equation, we know this beam is going to start to crack at that point. If the total load is going to be lower than 781, it means this beam is meant not to crack. If the total applied load as service load, no load factors here. We're not trying to find out Feynman, the strength. We're doing here serviceability check. We'd like to see when do you think the beam is going to crack, or this is meant to be free of cracks. So now let's look at the moment that we're just talking about. Keep this number in mind, 781. Moment due to dead load. So if you just put the dead load, no cracking, because you look here, 781. If you just put this beam on two supports, one at each end, without any additional dead load, without any live load moment, the beam is not cracking because this number here is going to be smaller than this number. So I'm going to say, how about if we add the superimposed dead load to the dead load? I'm going to be taking this 52 plus the 207. I'm going to end up with 260, which is going to be this. Let me just go here. It's going to be this number here. So once I apply here the dead load and superimpose dead load, I'm going to be at 260. It's still much lower than the cracking moment. So if you put the beam supported in 2 points, and you start to add also the concrete topping or whatever that you have there, and the piping and the whole thing, right? You're going to still below cracking point. But look what happened once you add here the live load. You're going to be adding this big number here, 580. Now you bring it here to 841, which is more than the cracking, which means the beam is not going to crack under its own weight. It is not going to crack under its own weight, and the superimposed dead load is going to crack once you add the live load to it. So it says here the beam will crack once the live load is applied. Because guess what? Before the live load is applied, you are at 260, and your cracking point is going to be 781. Once you add the live load, now it becomes 841, which is higher than this cracking point. So we know that this beam is going to crack once you apply the live load. Now, do we have an overload moment? Are we going beyond here the cracking point? I'm going to say yes. Your total moment is 841, and the cracking is going to be 781. Difference is 60, about 60 kfoot. So this is what we call here the overload moment. Like the first numerical example I gave you. I said total moment applied is going to be 100. The cracking moment is going to be 80. So the overload is going to be 100 subtracting 80, which means after the beam is going to crack, you have this additional 60 kfoot beyond the cracking point. So, okay, simple analysis, I guess. What is the safety factor now against cracking? You're going to be taking this load here, 781, which is what? The cracking, you divide by the total load. It's going to be 0.93. This means that this beam here is meant to crack under service load. If you have a beam that's meant not to crack or designed not to crack, I'm expecting here safety factor is going to be at least 1.0. So if you see here a value of 1.5, what does it mean for you? It means at 2/3 of the load, right? At 2/3 of the load, or 2/3 of the cracking moment, the load was right there. In other words, the applied load here will cause a moment which is nearly 2/3 of the cracking point. So you still have way to go. Now you think, and then you say, if I have here additional load of nearly 50% of the given loads, which means the demand, right? The beam is going to be right there at the cracking point. So if my intention to have an uncracked beam, I'm going to be very satisfied with a factor of 1.5. Because I'm going to see here, with 1.5, I still have long way to go in terms of the loading. If it is equal to some number here below than 1, like for example, 0.93, what does it mean? It means that the beam is going to crack with the given loads. It's going to go here beyond the cracking point by nearly 7%, because this here means 93%. And after the beam cracked, you loaded by about 7%. This is the meaning of it. Any questions? Hello? Anyone there?
No, no questions.
No question.
Okay, thank you. All right, second example. Well, it seems to be the same beam, right? So first we studied just this beam, right? I'm going to be taking this and put some concrete topping, because usually this pre-stressed beams, after you install it in place, you're going to put some reinforcing in the top and then put some concrete topping. That's exactly what happened. Properties is going to stay the same for this beam section. It says here, consider 3-inch slab, 32-inch wide, just for the weight. Ignore the strength of the topping slab. Now let me go back also to the previous example and look at some stuff here. It says here superimposed dead load. What is the superimposed dead load? It says here 100 P left. If you take the weight of this slab, is going to be, this is going to be the 100 P left, just, you know. Look here for the loads again. Dead load from the chart, from the property of this beam. 100 P left. If you take here 3-inch by 32-inch by 150 divided by 144, you're going to end up with 0.1 K left. And the live load is going to be the same. It says here, you're going to have the same strains that you did problem number 1 with. You're going to have non-tension steel. It's going to be for number 6. Also, FPE is going to be 155, not 150, like the standard value. This modulus elasticity for the pre-stress strengths is going to be 28,000 KSI. Usually, the one that we have for standard steel is going to be 29,000. But here they say, well, it's going to be 28,000. So, okay, we'll just use this value. The centroid of the strengths is at 15-inch below the beam CG. So, okay, I understand that. And the non-pre-stressed steel is going to be at 1.5-inch clear. From what? From the bottom. It doesn't say from the bottom, but I know where this non-pre-stressed steel is going to be located at. And then it says here you don't have any compression steel on the top, so don't do AS prime. They ask you first to do the factored moment M sub U and then do PMAP, which means complete design now of the beam. Okay. I have dead load, I have superimposed dead load, I have live load. I can figure out the moment, which is going to be very similar to what we have done in the previous slide. Exactly same numbers. So moment due to dead load is here, due to superimposed dead load is here, due to live load is right here. Now, ultimate moment is going to be equal to 1.2 dead plus 1.6 live. Someone's going to say, why don't you try also 1.4 times dead load? I say, it's fine, but look at these two values here. They're going to be very low. See this 207 and the 52, much smaller than the live load. So no way that 1.4 dead load is going to be controlling my design. So what I'm going to do here, I'm going to be adding this dead load to superimposed dead load, multiplied by 1.2 plus 1.6 times the live load, and this is going to be the moment I need to design my beam for. So now I want to be sure that this Vman is going to be greater than this M sub U. Okay, great. Going back to this previous slide, you're gonna have this FPS, which is a nominal failure stress. And I have two ways of doing it. I have a detailed method, or I have an approximate method that I should be able to use. Now, in our case, we're gonna have tension force coming from the pre-stress and another tension force coming from the conventional rebars, like the 4 number 6s. We're gonna be doing very similar to what we have done in conventional concrete beam design. You find out the compression block depth, find out the compression force, you're gonna set it equals to T due to the pre-stress and T due to the conventional rebars, and then you can complete the analysis. The point that we're interested in this case, we're not interested in during rigging or moving the beam. We're not interested right after the pre-stress. We're not interested in checking the service load case. We're interested in the capacity. So we're right here at the last point. So we're not doing here any of the checks that we used to do. We're just after finding out the capacity Pmn of this beam, which means this distribution of forces. So, okay, APS, we have done this before, the nearly 2 square inches for the pre-stress strains cross-section area. You can see here, P sub E is going to be equal to this cross-section area multiplied by the 155 KSI. Same thing that we have done in problem number 1. The multiple elasticity, 28,000 KSI. Now the question is, how much strain that we have here in the strain itself? Because look what happened. In order for you to put this anchorage at each end, you need to stretch the beam to a certain distance. And the same amount of strain that you gain in the reinforcing in the strands is going to be the same amount of strain that you impose on the concrete. Because at the end, the length is going to be the same. So the strain here in the strands is going to be equal to 155 KSI. You divide this by 28,000, and you're going to end up with this number here. So this is going to be the strain in the strands at PE level. Now, this strain in the strands is going to be also applied to what? Applied to the concrete. And the amount of concrete, amount of pre-strain force here that you put on the concrete is going to be equal to 308. Where is this number coming from? I'm going to take you back here. I'm going to say it's going to be this number. So what happened in reality, you said, if you apply this amount of stress on the strand, I'm expecting to have this much strain. I'm expecting also the strain in the concrete to be the same. But look what happened. When you look at this equation here, and this equation, with this you can determine the strain in the concrete. And then you look at the strain in the concrete, you find it's going to be 0.0004. So I'm wondering, what does it mean by that? Does it mean that the concrete is going to be strained at this level, the 0.0055, or at 0.004? It's going to be the question, right? And then we need to look at what happened. So right at the strained location, the strain in the concrete based on this equation is going to be equal to 0.0004. But in the strand itself is going to be 0.0055, which means it is true that you stretch the strand. And then you look here at the amount of compression that happened in the concrete. At the beginning, you think that strain in the concrete is going to be the strain in the strand. But this is not true. Look at the big difference between the two. How many times bigger? At least 10 times, am I correct? Right?
Yes.
Yes.
Now, if you like to understand this in a simpler way, you say, let me assume here that I'm going to have here a rubber band, just a rubber band. Stretch this rubber band. Consider this to be your strength. And then after you stretch it, you're going to be put 2 anchors, one at each end. Now, at the beginning, the rubber strand had lots of extension. I understand that. And the amount of strain in the rubber strand is going to be really high. Now, at the end, the force that you have in the rubber strand case is going to be very small because the rubber strand is not really strong. Now, after you put the anchorage or you put your fingers here at the end of one of these beams, and then you think that now you put enough pressure because the rubber strand now wants to bring your hands closer to each other. So you're going to be saying, is the strain in the concrete going to be the same as the strain in the strands? And the answer of absolutely no. They cannot be close to each other because you stretch the strands, the rubber bands by a lot. So the amount of strain that you put in the strands was a lot. But the resultant force that you put in the concrete was not that much. It was just your fingers when you put the anchorage. And this amount of force is not really causing loss of strain in the concrete itself. So again, just to make it simple, or to put some reasons for why the strain in the concrete is not the same as the strain in the strands. The strand multiplicity here, look at this. At this value here, 28,000 KSI. And when you look at the concrete multiplicity, 4,000. Compare 4,000 to 28. And with that, you're going to start to have the feeling why the strain in the concrete and the strain is not the same. You have taken the same force, and this force is equal to 308. Let's say that you don't have this pre-stress, you don't have eccentricity effect, you don't have any of that. Let's just say that you apply here a uniaxial force or stress to some given member. One of them is going to be concrete, the other one is going to be steel. The one made out of steel, it has a modulus elasticity of 28,000. The other one made out of concrete, it has 4,000. So which one do you think is going to strain higher? Look at this. The strain, the strain here is going to see less. Because look what happened. When you take 155 divided by 28,000, take the same force. Let's say here's the same force, right? You take this force here. You divide by the cross-section area. In order for you to get to this number, what do? Let me put it here. See, this strain is going to be equal to the force divided by area, right? Multiplied by E, the multiplicity. Don't you do that? So first, you do the force divided by the area to get you stress. And then you divide the stress by E. This is exactly what you're doing here. You take the stress divided by E. You get some strain. So if you just take concrete, a piece of concrete, it has the same cross-section area as the piece of the steel. And you apply the same force. Which one's going to strain more? Look at this. The strain is going to be equal to the same force. You divide this by the area. Area of concrete and steel is going to be the same. And then you divide again by E. So the stress is going to be the same. Once you divide by E here, you'd expect that the strain in the steel is going to be much less. Now let's see the actual example. What do we have in our pre-stress beam? Now our pre-stress beam, the cross-section area of the pre-strand, the strands or the pre-stress strands is actually very small. It says here 2 square inches. It is almost nothing. And look at the area of the concrete section. Look at this area here, 377. How many times larger than the steel? Just take this number here, divide by 2. You're talking about 160, 170, 180. This is going to be a big number, right? If you have here 380. So you're talking about how much? See how many times? 190, 180. It's going to be a big number. So it is true that someone's going to be thinking here and say, the multiplicity for the steel is going to be really high, which means the amount of strain in the concrete is going to be in the steel is going to be much less than that of the concrete. But because the cross-section area of the concrete is much larger than the strands, which is 2 square inches, you're going to see here that you have more strain in the steel than the concrete. Does it make sense? Yes?
Yes.
Now let's look at the section. In this section, I have the depth to the strands is going to be 36,116. The depth to the concrete is going to be 37.6. How do you calculate this out? You have here 4 number 6s. You have this much clear cover as given the problem. So I'm going to take you back here to this problem. It says 1.5 inch clear cover, and then you have 1/2 of the bar diameter, right? So with that, you should be able to get to this 37.6 inches. DP was given to us in the problem. It's going to be at 36.16 inches. It's going to be the centroid of all of these strands. You see the strands? They are not just in 2 layers. And this is going to be the location of the centroid of all of the strands. So it's going to be right here. If you like to figure out exactly where the 37.6 coming from, total depth is going to be equal to h, the 40 inches. You subtract here 1.5 inch clear cover to the tie, and then you have 1/2 inch for the tie. And then you have number 6 divided by 2 to get to the center of the rebar. And with that, you have 37.6 inches. Now, your eccentricity was given equal to how much? It's 15 inches. You guys remember C sub CT? How much was C sub T? It is equal to 2116. Where is this coming from? It's from here. Let me take you back to it. 21.16. What does it mean by this number here? This number is going to be the distance from the centroid of the section to the top. It's going to be this number here. Now it says the drape from this point here is going to be 15 inch down. So I'm going to be taking this 15 inch plus 21.16, which is the top from the centroid to it. So I have here 36.16, which is this number here. APS that I just calculated out, I'm just going back here to it, is going to be almost 2 square inches. But AS for the conventional rebars is going to be 4 number 6s. And I have 0.44 for 1 number 6. I have total of 1.76 square inches. So now I have AS. If you guys remember beta 1, compression block depth compared to the neutral axis depth, you have the ratio here of 0.8. Why? Because you're at 5,000. When you're at 5,000, you're going to be nearly right here. It's going to be 0.85 for 4,000 or less, and for each 1,000 psi, you're going to be losing 0.05. So it's going to be 0.8. Now let's try to figure out here the compression block depth. So I have my nice equation here. It's going to be the tension in the strands plus the tension in the conventional reinforcing divided by 0.85 F prime C times B. Now let me look here at each one of this component and figure out the value for it. APS is going to be 1.99. FPS, we said that we're going to have a code equation, but for now, let me assume it's going to be 205 KSI. So I'm going to be taking this value. It sounds to be a good value, 205 KSI. If you like to use 200, this would be okay at the beginning. There shouldn't be a problem with that. AS, the 176, this is going to be 4 number 6s, right? And then 60 is going to be the yield strength. Divided by 0.85. F prime C is going to be the 5 KSI, and the width of the compression section of the beam is going to be 18 inch. Now let me take you here to the section so that we understand where is this 18 inch coming from. It's going to be right here. Meaning, if the A value turned to be right here within the first 4.5 inches, I have no problem because I consider here this to be 18 inch. But once the compression block is going to be going through this section here, any of this location, it means my assumption was incorrect. It's going to be like treatment of a T-beam. If you remember the T-beam analysis, when you have a T-beam analysis here, if A is going to be within the plane thickness, you're fine. It's going to be a rectangular section. But once this A, look at this dashed line. If A is going to be falling here, and C is going to be falling here, you cannot really say it's going to be 18 inch for the width, unless you'd like to do some kind of approximation if you want to. And look at the big difference between this. On the top you have it 18 inch, and here you have it at 6 inches. So it is not like 18 to 16 or 18 to 12. No, it is from 18 to 6 inches. This is going to be 1/3 of the flange width. So okay. Now I know where is this 18-inch coming from. I did my analysis. I find out that A is equal to 6.71 inch, which is less than 8 inches. What is this 8 inch? Let me look again. What is 8 inch? Is going to be from here to there. So actually A turned out to be right here. And the C is going to be right here. It's going to be the web. Because C, you're going to be taking this, the depth, which is this A divided by 0.8, the beta 1 to get to C. So you say, okay, here's the C. It's going to be 671. And then you divide this by 0.8. It's going to be 8.39. Now the question is, are we satisfied with this, or do we need to treat it as a T-beam? This is going to be the question, right? If we assume that you're going to have here a smaller width, would that result in a deeper or higher A or lower A? This is going to be the question. Yes?
Can you repeat that one more time?
Okay. If I consider here that the width of the flange is going to be smaller than 18-inch, which is the case, right? It's going to be actually smaller than 18-inch. Would that result in higher value of A or a smaller value of A?
Higher.
Higher.
Because you are pushing this down, right? So, okay. You just need to have the feeling and understanding of what's going to happen. Now, how about the strain in the strains? Do you think it's going to be higher than the yield point, the 0.02? You know this chart? To find out the phi factor? It depends on C over D, if you like to do here C over D, or the strain and the strains. It's going to be one of the two. Because you'd like to figure out here the phi factor. If you're going to be in the tension control, which means that you have lots of tensile strains in the tension rebars, or C over D ratio is going to be very small, your phi factor is going to be 0.9. So I'm going to take it back here. I'm going to go back and try to figure out the strain where? In the strains, by doing this two similar triangles. So I'm going to be taking it back to here. I'm going to say, okay, where's the strain distribution? Let me look at the strain distribution. This is going to be my datum, which is going to be right here. And here's the strain distribution. It's going to be exactly like this. Right at the C depth, the strain is going to be equal to 0. Right here in the top of the concrete, how much this is going to be? Someone help me with this? Yes? Can someone help with the strain at the top of the concrete?
0.
How much?
0.00.
0.00?
0.003.
3, yeah. Now the question is, how much is the strain? So if this is going to be the neutral axis, because it's going to be the C, this means it's going to be the intersection point between the datum and between the strain gradient. How would you find out here the strain at dP? You say the strain at dP, which means this value from here to there. I can do it like this. This is strain. If you take this strain here divided by 0.03, it's going to be equal to dP minus C. dP minus C is what? It's going to be this length divided by C. What is C? C is going to be from here to there. So you have here two similar triangles. You take the strain in the steel divided by 0.03 is going to be equal to dP minus C divided by C. Or you can say this is strain in the steel divided by D minus P is going to be equal to 0.03 divided by C. You have the dP value, you have the C value because you have just solved for it. You have the strain of the concrete, the 0.03. Now you should be able to find out the strain in the strains. Exactly what happened here. Here is the strain in the steel. And look, you have really good value, 0.01. This gave me more than 0.05. So absolutely, you have here one of these cases is giving tension control. You are more than 0.05. So your phi factor is going to be equal to 0.9. Okay. How about the strains themselves? From the amount of pre-stress force that you put in there. We have looked at this before, right? We have done this before. So this value that you're looking here at is going to be right when the depth of the neutral axis is going to be at this point, which means it's going to be at the ultimate point, the capacity point. And this C depth is going to be based on the same value. So we're here looking at the capacity point. So the strain in the steel at the capacity point equals 0.01 at the capacity point. But the steel here, the actual strain, when you put this force to it, you're at 0.05. So what's going to happen? When you apply the pre-stress to the strains, you're going to be right at this value here. You're going to be right at this amount of strain. But if you apply more load to get very close to phi man, the strain is going to be equal to 0.01. So there's going to be here significant change in the strain between the point where you have the effective pre-stress on the strains and the point of ultimate, which is the capacity point. Let me take you back here to this previous slide to know what's happening. I'm talking here about this one. The strain at this point here is going to be equal to 0.005. And the strain at this point here is going to be 0.01. This is what I'm talking about. What happened between this and between that point? You're adding more load to it. It's going to be just the surface load. But because the load factors, as if you're adding more load to it, so the amount of expected strain at the ultimate point, which means the capacity point, is going to be equal to that value that we just solved it for. So this strain value is going to be the strain in the steel, in the strands, at the capacity point. And this strain is going to be the actual strain in the strands that you apply when you apply the pre-stress force and after you lose the stresses. You have some losses, right? After the losses going to be taking place, you're going to be at strain in 0.005. Let's look here at the stress-strain relationship for the strands, which is completely different from that of the conventional rebar, because you don't really have an actual yield point, right? It is not well defined. It's not very accurate. So first, at the beginning, at the effective pre-stress, you're going to be at this absolute one, which is 0.0055. This is what you apply first. And now, because the concrete itself is going to be compressed, right? Now you put some compression on the concrete. And the concrete wants to come back because it has some resistance. And the amount of strain is going to be 0.004, which you just calculated that a few slides back. And the strain just coming from that source. What source? From the capacity point. When you apply enough loads, you're going to have this much strain in the strains themselves. Now the total strain that you're going to have here in the steel is going to be equal to the summation of all of the three values. You're going to be at nearly 0.016. So let me repeat this again. So first, you take the strain, you're going to put some here pre-stress, and you're going to be at this strain. So I understand this strain here. We're done with this. We're right at this point. Now, because the amount of strain that you put there, the concrete now is resisting. And the amount of strain that you have there in the concrete is going to be equal to this value because we just calculated this out. And due to the applied load at the capacity point, you're going to have additional strain of this much in the steel. When you add them all, this is going to be the total strain that you have in the strands. Now let's look here. Stress-strain relationship. The strain is given the x-axis, stress is given the y-axis. So what do you do here? You're going to come here with a vertical line at this given strain, 0.016, and look at the amount of stress. It is about 229. What did we assume for this value? Anyone recalls?
205.
205. Assume low value, and it turned up with a higher value, which is good. You don't want to assume 220 or 230 and end up with only 200. Like, for example, this value here for the yield stress. If you remember here the way that we design conventional concrete, if I assume this to be 80, and then at the end when I'm running here my analysis, confirm now this turned to be 60. You see, this is not good. But if I assume this to be 50, and then at the end I'm going to have here more tension force, I'm going to be happy because my fee man is going to be harder than what expected to be. I said, okay. This is kind of detailed method of finding out FPS, because FPS here is going to be based on the amount of strain, actual strain that you apply to the structure or to the beam. But I want to run here with you this. I mean, I want to show you this, run this by you guys. You guys have seen this slide before. This is not a new slide. This is going to be for FPS based on FPU, and this factor here is going to be less than 1. And this is what the ACI is telling you to do. So usually in our design, we don't really do this. This kind of detailed method that you're trying here to do maybe a software or do maybe some research. So you're going to be figuring out the strain in the concrete, the strain originally in the strands, and then you find out the stress-strain relationship, right? And then figure out FPS. But if you like to use this equation here, which is going to be much simpler, and we went through this tables before, that FPY divided by FPU is going to be 0.85, and for that, this gamma P is going to be 0.4. So this gamma here, P is going to be 0.4, and the beta one is going to be the 0.8, goes with 5,000 PSI of concrete. If you like to use this equation, which is a code equation, look what happened. Here is rho, the steel reinforcement ratio. You take the 4 number 6s divided by the cross-section area of the concrete. You take rho P, is going to be the 1.99, 2 square inches for 13.5 inches strength, divided by the same cross-section area. And then you solve for this equation, you end up with 231 KSI. So I'm going to say, okay, it means the ACI code is going to give me here 231 KSI based on this analysis, right? Based on this quick equation. And if you like to do detailed analysis, you're going to end up with how much? 229, not bad. Very close to each other. This now gives me some confidence in the use of this equation. So I'm going to say, using this equation is not a bad idea. I should be able to use it. And I'm going to end up with maybe 231 KSI. And effectively, I should be able to use 225 if I want to. Or just keep it like 230 KSI if you want to. Make sense what I'm trying to say here? I'm trying to tell you here, finding out the value of FPS, you can do it in 2 ways. One way is just use a code equation, which is this equation here, right? Another way is to do detailed analysis. And by doing this detailed analysis, you figure out the amount of strain that you have at the effective point, right after the losses, find out the amount of strain in the concrete as a resistance, and find out the amount of strain in the strands due to the applied load when it gets close to the capacity point, add them up all together, look at the stress-strain relationship, and then you find out this FPS from the chart. This is going to be more detailed analysis. So you can have it either way. If I'm doing here this for an exam or doing it for a homework or doing it for a project, definitely I'm going to be using the ACI code equation. I'm going to be using this. And if you like, here's the detailed analysis for it. I'm going to say from slide 39 to slide 41. This is going to be the way that you'd like to follow it. No compression steel. If you notice here, rho prime is going to be equal to 0. This Fy is going to be 60. The depth to the reinforcing bars, 37.6. The depth to the pre-stress, DPS, is going to be 3616. F prime C, FPU, the 270. F prime C, 5 KSI. This row B and row is going to be the steel ratio for this row is going to be for the conventional rebars, and this is going to be for the pre-stressed rebars. Okay, not a bad idea to use a code equation. So let me now go back and see what's going to happen next. Now you understand that the amount of strain that you are going to have in this strains is going to be 0.01 at least. When you compare this 0.01 with this chart, you're going to be in this side, tension control, and your phi factor is going to be equal to 0.9. Okay, good. How about phi man? I'm going to use the equation given to me. I have this simple equation, which is very similar to the one that uses a conventional concrete design, but it has additional term for the pre-stressing. Let's try here the equation. The phi here is going to be 0.9. APS, the 199. 229 based on this analysis, right? If you like to use 230, it's going to be fine. You can use 230 based on the code equation. dP minus A over 2. Where's this A coming from? Take you back. Here is A. 671. Plus, this is going to be the strength coming from the conventional rebars. The 176 times 60, D minus A over 2. So actually, the A value here is going to be the same in both terms. It's going to be just the same A. And with that, you're going to have a moment of 1379 kfoot. How much was the moment demand? I have it a couple of slides back, 1249. So this design is good. This beam is good because it can support all the way to 1379, and the applied moment as a strength design is 1241 or 1242 if you like. I'm going to take you back here to M sub U. Here's M sub U. 1242. Any questions? Any questions here? No?
Yes, Professor. On the Feynman equation,
Yes.
why is the A 7.34 where on the previous slide it says it's 6.71?
I'll tell you the reason. This 7.34, if you remember this discussion that I said, this 671, what's going to happen when you use the actual width? What's going to happen to the A value? Do you think it's going to be growing up or reducing? When you go to this area here and be very detailed analysis.
It's going to reduce.
Is the A is going to grow up? I mean, if the A is going to be falling here, right? And you assume that you have here 18-inch, but in reality, you're going to have a smaller width. What's going to happen to your A? Do you think it's going to be more than whatever that you calculate out based on 18-inch, or is it going to be smaller?
Okay, so it's going to be more.
It's going to be more, right? Because now what's going to happen? You're reducing here this, right? So in this analysis here, because this is based off a software analysis, so I'm not showing exactly how to get to it, right? So the A value has just been increased. So 671 in reality is going to be this much, which is going to be this 7.34. If you'd like to go in more detailed analysis. Now, in your case, you're not going to be exposed to something like this because you cannot do this by hand. Just think about it this way. The way the software is doing it, it cut this into slices. It is taking the concrete beam and cut it into very small slices like this. It's going to be, let's say, 1/2 inch. And you can decide on the height of each slice, right? And then when it comes here, it's also going to be cutting this. Look at this. It's going to be cutting it like this, right? It's going to be very small segments. And each segment is going to have a different width. This makes sense to you?
Yes.
Because here's going to be 18-inch, and as long as now the software is going to start to use first 18 and then find out where this happened. And once it knows exactly that happens here, it's going to be taking this modified concrete section and try to use it. And then it's going to do through iterations. And this iterations is going to adjust the depth A and also depth C. So what happened here, I'm not showing all of this iterations because this is done through a software. I'm just showing here the final conclusion that based on hand calculations is going to be 671, but the reality is going to be 7.34. Good catch.
Okay. Thank you.
Good catch. Thank you.
Thank you.
Any other questions? All right, let's go to next. Here's a new slide set, which is mean about bridge concrete design, bridge concrete girders, and the big difference between this girders and between double T's, and just different industry. You know, you have design for parking structure beams and double T's versus residential buildings versus bridge beams and girders. So the same information that you have and the same design methodologies that we used to have for any other pre-stress beam or double T is going to apply here. This is going to be just different designation and different sections, if you like. Here's the standard bridge cross section, and as you see here, you have I beams, which is very similar to the I beam that we were just working with in the previous example. Actually, the previous example was for a bridge beam. It was not for double T. You know, you have seen double T analysis and you have done it in your midterm. It is not for precast beam, let's say in a parking structure. So it was exactly for this beam, right? One of these beams. Sometimes you have pre-tension members, right? And guess what's going to happen? Once you apply the pre-stress tendons, and once you cut the strands, what's going to happen now? You're going to be applying this camber. So usually you try to apply the camber to overcome the deflection due to dead load and maybe section or part of the additional dead load or superimposed dead load. According to Caltrans DPS, which means design bridge specifications, you have this California I girder. And if you like to look at this California I girder, they have charts. And with this charts, you're going to have different sections. It's going to be very similar again to the steel book that you have sections and you have the section properties. And they give you here, they say, well, that this is going to be good, possible for a span, if the span is going to be between 50 feet to 120 feet. But usually it's going to be good for the spans between 50 to 95. So don't push it to 125. But if you like to push it a little bit, if you have a longer beam or a longer span, go to this bulk T. In the bulk T, you're going to have here more space so that you can put the strands in there. And this is going to be more suitable when you go here to maybe 125 feet all the way to 150 feet. You have also the wide flange girder, which goes to maybe 180 or 200 feet when it comes to the span. This is here, the one that you're looking at is what you call the bulk T. And you see here that you have big bulk at the bottom. At the top, you have a small T. And this gave you the wide flange girder. This goes here to longer spans, much longer spans. This one here, if you look back in this, it says goes to 150. But if you like to go to longer spans, like 180, maybe you'd like to go to one of these. Because you have here more room that you can put enough strands, and also the flange is wider. And as you see here, you have lots of rebars that sticks above. And you see this rebars, the dowels. This because if you go back here to the bridge section, now you'd like to connect this bridge deck or concrete slab to the beam itself. And your only chance is to have some dowels between the two. That's why you see here some rebars that goes like this in both sides. Right? Sometimes you have it also with some hooks. And then you put some rebars in the deck, and then you put the concrete deck. of the bridge, and with that you have good bond between the beam itself and between the deck. Look at this rebars. You stick them up like this, and then after that, once you put them in place, debend it to provide this hook. So it's gonna be like this, and also vertical is gonna be like this. So the rebar is coming like this. So they bend the rebar. This is here the wide flange, which is the same as this one here. This is really the big one. This goes all the way to 200 foot span. So this is really big ones. This pictures here is taken from the standards, the BDS, and then they give here, they say, well, here's one of the sections, and this called California I-36. What's California I-36? It means it's gonna be taken from the California standards. It has 30-inch or 36-inch for the depth of the beam itself. And it's gonna be just an I-beam. It's gonna be I-36. And look at the properties. You have all the properties. And here's the weight of it. Here's its top, its bottom, Y top and Y bottom, and the moment, the ICG, right? Moment of inertia, the cross-section area, and the total depth. You can go to bigger beam if you want to, right? And then you have here all the properties for them. It's gonna be for the I section or I girder. How about the bulb T? This is gonna be like the second phase. So the first one here goes up to 95, let's say about 100 feet. This one goes to 150 feet. Now you have here a big section, right? You can put more strains in this section. And then also you can do here post tension, which means when you buy this beam or when you fabricate it, it's gonna be fabricated with this pre-tension. So this is gonna be all the small ones gonna be pre-tension. And this optional post tension, it means that first you're gonna be moving the beam from its place, you're gonna be rigging it or transport it to the side of the bridge using this strands for the strength. And after you put it in place, you can add more post tension to it at the side of the bridge. So it is first like partial pre-stress, and then after you move it there, if you like to add more pre-stressing to it, you should be fine. But if the length that you order was good enough without this additional post tension, then you should be fine. You're good. And again, because it's called here California bulk T, it says here California, and instead of I, you have BT. And look at the depth. Depth starts at 49. It goes at 85. Look at this depth, 36, right? This is gonna be 36. It goes all the way down to here to 5.6. So this is gonna be here larger beam. And look at the width here, about 4 feet. Look at this width here, 19-inch. Now you understand and you have a feeling here for the difference between this one and between this one here. This one you have more area for the compression, which means your A value is gonna be very small and your moment arm is gonna be larger. You have amount of big area here, this is that you can put lots of strains, and then here you have much smaller area. So now it makes sense. It's gonna be cheaper, it's gonna be a little bit more expensive, but it goes all the way to 150 foot span. Now let's look at this bathtub. What is this bathtub? This can be for the box girder. This is actually what we call here box girder, because at the end of the day, you're gonna put here concrete slab. And you're gonna have lots of rebar that sticks like this for anchorage, right? And look also at this. Here's the U section, and of course, you're gonna have all of this strands for the pre-tension, and you're gonna have this ducts. Let me look here, let me zoom in. It says optional post-tension ducts, if you like to use it in lots of cases, right? And again, you have all of this section properties. This can be the wide flange. This is the wide flange that goes to 200 feet. Can I take you back here to this section? This is the wide flange here. Here's a picture of it. But here's the section properties. It's gonna be California wide flange, and look at the depth. Depth will start at 4 feet. This is the one here that goes to 200 feet. And lots of strands. As you see here, you have many strands in this case. And for the depth, it goes to 10 feet. Just imagine this. For the size, it's gonna go here to 10 feet. This depth here, just imagine this. It's gonna be 10 feet. A lot. This is really large. You have more sections and more stuff. You have this California post-tension wide flange PT girder, right? And also you have this option of having this post-tension if you want to. So now I hope that you guys are clear on the meaning of this partially pre-stressed in partial pre-stressed, usually the way it works, you put some pre-tension strands, and this pre-tension strands is going to be able to help you out to move this giant beam or girder from the fabrication side to the bridge side. And after you put it there, in order for you to gain the strength for the additional life load that you're going to be adding and the additional dead load that you're going to be adding to this beam, you're going to have all of these ducts. So you can do first pre-tension, and then after that you put the post-tension in these ducts. You have also this core slab, this like the voided slab, and I guess we have seen stuff like this. And the reason that I'm just going fast here because I'm not going to have any examples on this, so I don't really need it. It's just going to be for your information, so that in the future, when you see one of these sections that you need to do the analysis for, you need to know how to read it. You need to understand the cross-section area. It's going to be very similar to the one that we have in the PSI manual. Moment of inertia, Y bottom, Y top, section modulus, and the R, and the weight is going to be exactly the same. There's no difference here between the two. You're going to have similar information. Now, this one we call here about the design load and the design stages. Now, I'd like to stop here. This can be right at the middle, right, of the slide set. And I'd like to show you here, what do we have for the project. Have you guys seen the project files?
Yeah.
Okay. Here's the project statement. You have 5-story parking structure. The story height about 11 feet. This is built in the city of LA, and this will be the adopted code, which is based on the CBC 2019. What we're going to be doing, we're going to be designing the double T's and the beams and the columns. So when it comes here to design the double T's, we're going to be just taking one double T, right? Come to the beams, just design one. I'm not interested in designing more than one beam. Same thing for the column. We're going to be taking all the columns, just design it. Now, material properties. It says here it's going to be 5,000 psi lightweight concrete. Now, this is going to be important because you need to figure out the weight for the double T's. For the beams, it's going to be 5,000. It doesn't say here lightweight, which means you're going to be using here 150. How about for this one here? What should I use for the unit weight? I'm going to leave it for you because you need to look it up. You're going to pick one of these double T's from the PCI manual. And if you go here to lightweight, you're going to see here the self weight of the double T. So you don't really need to know if it's going to be 100 PSI, 100 PCF, or 117 pound per cubic foot. You don't really need to have this information for the double T itself. You may need it for the beam. So I'm going to say here for the beam, I'm going to be using 150 pound per cubic foot PCF unit weight. For the steel, we're going to be using grade 60 conventional rebars, and for the strands, it's going to be 416 grade 270. You're going to have some additional dead load, which is 10 PSF for mechanical, like miscellaneous piping, ducts, fixtures, and the life load is going to be following the code. So we need to look up in the code and see what does mean by parking structure, like commercial parking structure, and what does mean by life load in this case. Is the life load for parking structure, is it 50 PSF or 40 PSF? I want you guys to look at this. Right? The life load. Now let me show you here the plan of this parking structure. This is already built, so it's already constructed, right? This here says level 2 to level 3 framing plan, and then I have another picture that shows the upper level, but they're all the same. There's no big difference between the two. Looking here at the columns, see here I have column, right? You have some columns. And then this give me a ramp. So this area here is flat. You have elevator, which is right here, and then you have the staircase. And this usually, this staircase, usually you do it out of structural steel. So you're gonna have your structural steel. And this can be the elevator. That's why you have this hatch. It means it's gonna be open throughout. This side here is gonna be also almost flat. There's no slope in here. And this side, it's not really landing, but it's gonna be this area of the floor plan is gonna be flat. This little area here, it's like transition, it slopes down. So this is gonna be the big ramp. Just, you know, this is gonna be our big ramp. It's gonna be like this. This goes up and the other one goes here down. Now I see here some beams on the perimeter and some beams here in the middle, but I see here's two beams. Why? Because one of these ramps is gonna be going up, the other one's gonna be going down. So let's say just imagine that you drive here and then you go down and this is gonna be flat and then you go down again. And here's a double T. Here's one of the double T's. It runs from here to there. And this is gonna be the rip of the double T. When you look at the plan, this is what you see here. You see two rips. It's just vertical rips. It says here in the topping slab, you have 3.5 inch minimum concrete topping slab. Usually when you open the PCI manual, you're gonna see only 2 inch. But because in California, we really need 3.5 inch for the diaphragm action. Because we need to use it for the seismic. This is gonna be our diaphragm. It's gonna be only that 3.5 inch. And then it says here, with this reinforcing each way at center line of topping slab over precast members. What's the precast member now is gonna be this double T. So what I'd like to do first is to design one of these double T's. Someone's gonna say, well, this double T is just continuous. So you may have another double T here. I said, I understand. And also when you come down here, you could have another one with smaller span, right? And maybe this area here doesn't need double T's. Maybe I can just do blanks. And the same thing here. Say, fine. Just gonna be taking one and design it. If this is gonna be making more sense to you. I don't want to do the entire thing. Now let's look at the next two levels. Same thing. Exactly same thing. It's gonna be level 4 and 5. I'm gonna be interested in designing one of these double T's, and this is what I'm gonna start with. Now let's look at submittal number 1 and what is needed in submittal number 1. First, I'm looking for the load criteria. What's the load criteria here? Load criteria, we need someone to come here and then say, here's the dead load, here is the life load, and here's the additional dead load. When it comes to the design of the double T, it needs to be at the end as a pound per linear foot. So it says here, you need the load criteria for the double T. So first you can have it as a PSF and then convert it into PLF for the design of the double T. How about the double T? I mean, what size should I consider here? It says the span is gonna be 64 feet. Where do you have this from? I'm gonna say from the plan I just showed you. Consider it to be for 64 feet. I know that there's some smaller values, some smaller spans, but this is gonna be the span that I'd like to use here in my analysis. It's gonna be 64 feet. The depth is gonna be 24 inch. So now you can go to the PCI and pick 24 inch deep, double T. The one that has a flange width of 8 feet. So some of them, they can have flange of 10 feet. I don't want that one. Also, I'm looking for the lightweight concrete. So now we know exactly which one to pick. Am I correct in my statement here, or how do you guys feel about this? Would you be able to open the PCI and pick the double T that has 24-inch depth and a width of 8 feet made out of lightweight concrete? Yes?
Yeah, we could do that.
Okay, good. The strands are anchored at the CG location at the supports. So right at the support, the strand is going to be at the CG, the center of gravity of the section. And this says here, the strand is going to be located 3 inches from the bottom. Now look at the bottom of the double T, and then you put the strands at 3 inches. The maximum balanced load is nearly 90%. I guess we're now good with the balanced load. We know how to do this. Of the double T self-weight. So look here at double T self-weight. Do 90%, right, to be the balanced load and figure out number of strands. And you need to understand what is the reason of this balanced load, because you'd like to avoid the camber of the floor surface. This is why you go here to 90%. If camber is not an issue, maybe someone's going to do it to 120%. And all of a sudden you see the double T's like this, goes up. And to avoid the deflection, because deflection is going to be an issue, you do it, let's say, to 90%. So 90%, what you're saying here, I don't want to take it to 100%. Otherwise, I may end up with some camber. Also, I don't want to see loss of deflection. So I'd like to eliminate the effect of the deflection due to self-weight. This is the reason that you go here to 90%. Now the question is, determine the proper number of strands. And it needs to be an even number. Why? Because when you have double T, when you have 2 of them, you need to have the same number here and same number there. So don't, for example, don't go to 13 strands. It needs to be either 12 or 14 or 16. It's going to be usually an even number. After you pick the number of strands, based on this, you're going to be doing check on the stresses. At the initial pre-stress, at the service load. I guess by now we should be good about this. We know what this means by check the stresses. It means figure out the stress due to FPI and due to FPE. And then here is going to be with only the self-weight, and here is going to be with the total loads. Life load and dead load, and additional dead load. So we're going to be here a case of checking the stresses. You want to be sure that you're not going beyond the code limits. The ACI, they have limits. So you want to be sure whenever, whatever number of strands that you put in there is good enough so that balance, let's say nearly 90% of the double T self-weight, and also at the same time, you're not going to be cracking or damaging the double T before you bring it to the site and start using it. At the end of the day, you need to check the flexure's capacity, which means that you need to find out here PPN compared to his M sub U. M sub U is going to be based on these values here for the double T. Any questions? Questions about the double T?
Will the live load be on the PCI or no?
No. The live load is going to be in the EGCE 710 or 16 in the CBC.
And the ADL
Do you wanna,
is.
do you want to Google it? Do you want to Google it now and say parking structure live load
Yeah.
in California Building Code in CBC? What does it say? 40 or 50? Do you know the UpCode's website?
What section is
No.
that? 16, right?
This is going to be chapter 16, yes, of the CBC. But in the AC 716, it's giving the live load. Live load, I guess, in chapter 2 or 3. If I'm not mistaken. Did you guys find it?
It actually has a dash, like.
What does it say?
Oh, C residential.
No, we're talking here about parking structure. Yeah. So let's say commercial parking structure, like the way I mentioned. Good. Tristan, you went to the opcodes. Very good. It's going to be very useful website. We use it all the time. So what value would you use? 40 or 50?
I'm looking at the ASCE 7. It says 40.
Okay, very good. It's right here. Do you guys see it? Garage, passenger vehicles only is going to be 40 PSF. You guys see it? So it's going to be right here. Like any other commercial parking structure, it's going to be 40 PSF per square foot. It used to be 50, just so you guys know. That's why I said, is it 50 or 40? Because I want you to dig for it. But now we did it together. So this is going to be in this table of the ACE. So any questions on the design of a double T? Now here's the question. Can you use your spreadsheet?
Yes.
Why?
Yes.
I mean, does it say here anything about the use of a spreadsheet? Yeah, it says you should be able to use a spreadsheet or any software. If you are able to find any software, yeah, I mean, you should be fine. You should be able to use it. And your submittal here needs to be in PDF, right? And the Excel spreadsheet, if you're going to be using one. So feel free when you want to check the stresses here. This is going to save you lots of time. If you have it already available, this is going to save you here lots of time in this step and this step, right? Because I know that I talked to a few of you guys, or many, if you like, call it many, and they have a spreadsheet who can do the balanced load and do all of this. So this section should be a simple section for them. You can do it very fast. It's going to be only the new thing about the flexural capacity, which you can also add it to it if you want to. And this section is going to be exactly the same as this one here for the beam design. Look at this. It says here, determine the proper number of strains and check the stresses. It's going to be exactly the same thing for the beam. Now, when this is due, is it this coming Sunday? No, it's going to be at April 4th. So you still have good time before your to. Now, information about the girder that you're going to be doing there, it says here the width of the beam is going to be 24 inch and the depth is going to be 36 inch. So it's going to be a rectangular section. So you don't really need to look for a section for it in the PCI manual. I'm telling you here, take the width of 24 inch and the depth is going to be 36 inch. Now, what is the CG is going to be about? The CG is going to be about 12 inches from the bottom. Yes, Ola, go ahead.
Professor,
Yes.
you said it's due on April 4th?
Yes.
Okay.
Should I make it a little bit earlier or you're good with April 4th?
Earlier we have spring break.
Yes.
Yeah.
So do you have a spreadsheet to do this for you or not?
I do one with Ammar.
Okay.
Maybe I have to check more because
Okay. So who did most of it, you or Ammar?
we did it together, but for sure Ammar more.
Okay.
He said that he liked this precast and concrete stuff.
Because he's doing the spreadsheets, right?
No, we do it together, to be honest. But he
Okay.
do more.
Okay, I didn't hear you well, and I guess I'll forget what you have said. right after I'm done with this lecture. You
Sorry.
guys, I'll just forget what you have just said, that he did most of it, but this is fine.
Yeah.
You're good.
Shouldn't say that. Shouldn't say that.
Yeah,
All right.
he helped me. Thank you.
Okay. All right. Well, as I said, you should be also able to use a software, right? So I'm open for a software. So if someone has done the spreadsheet for you, it's okay for you to use it. I have no problem with this. So you guys should be fine. Because at the end, it's gonna be, when you do a design, you need to look at certain stresses, right? So if you're gonna be doing it by hand, which you have done it before by hand, and you have done it with your spreadsheet, so now you understand it, and also you have done it in the midterm, which means that you have done it at least once or maybe 3-4 times by hand. I'm okay with, if you guys like to use a spreadsheet. I mean, it should be absolutely fine with me. I have no problem with that. All right, any questions on this submittal?
Professor, can we submit it on 8th of April?
Oh, you mean the Thursday?
Yeah. Because we have spring break, we have plan.
Oh, but do you think in 4 days you should be able to finish it? Just wondering. It's just a question.
No, actually, because I have planned spring break, that's why. So it doesn't matter like 4 days or 3 days. That's why.
Okay. Is this good?
Yeah, thank you very much.
No problem.
Thank you.
No problem. You know what? This is needed on April 8th. How about that? So I'm gonna change this on Canvas and post it again. Make sense now? You guys follow what I'm doing?
So, yes.
So you mean this part on April 8th only?
Yeah, this section here, this shaded or highlighted section
Yes.
is given April 8th. And
Okay,
this
and
one
the rest-
here is gonna be the next, right?
Okay.
But if you decide to do the whole thing, if it's gonna be that easy for you, because once you're done with this, you should be able to do this, you know. But let me give you here more chances that you enjoy your break,
Thank you.
right? So I'm gonna do this 2 sections for April 8th, and this gave you the following, the beam
Okay.
design. So you just do the double T, and that's it.
Okay, and just in case if we could finish it, we can, and if we cannot, we can do it later, right?
Which one? Say it again.
The second part, the beam design.
Yeah, no. I will change this submittal here. I'll change it and repost again. Your
Okay.
submittal is gonna be only from here to here. This is gonna
Okay.
be the first submittal. It's gonna be
Okay.
second submittal. So I'm gonna repost this again. So please, if you download the file, just delete the file that you downloaded and re-download it again. I'll try to do it tonight. All right?
Thank you.
No problem. Any questions before I let you go?
Yes, Professor. Is the floor plan available as well for the
Yeah, it's
project?
posted there. Yes, it's there.
I can't find it. I just see this part, the project submittal one,
Oh,
but I don't see the other part.
It says here submittal one, but right above submittal one, let me look it up again. I go here to assignments, and then it says project. When it says project, there's a section called criteria. Did you see this criteria thing? Or no? No.
Yes, I see it now.
Okay, let me show everyone what we're talking about. Where is this at? It's right here. Okay. Look here at the bottom, it says criteria and then submittal one. When you open criteria, you're gonna see a bunch of stuff, all of that, right? So what I'm saying is, do not download this section of it, which is the submittal one. I'm gonna change it and repost it again, okay? So I'm gonna redo this again. Criteria is gonna be the same. I'm not gonna change it. All right, any questions?
Professor, I had a question related to the exam, but I don't want to keep everybody here, so I don't know.
Okay, go ahead.
Well, it was mostly about the part with the live load and the load, you know, because we had like part of it was belonging to the untopped and part of it was for the topped part.
Yeah.
So I don't know if we can go over that. That's why I knew.
Okay. So let me tell you what I'm planning to do. I'm still grading the exam. And once I'm done, as I said, that I'd like to meet with each one of you guys separately so that I go through the exam with you. And if you have any questions, if you have a general question and you think it's gonna be okay to share it with everybody, and I'm sure that maybe others have the same question, right? This is gonna be okay. But if you like to keep it when we meet, because you know, this business of education during this pandemic is gonna be really tough to evaluate students, right? I'm sure that you agree with me on this, because most likely everybody would keep his mic quiet. He's not gonna turn it on, and I cannot just use the performance of the exam, the written exam. So I need to have kind of an oral exam, or I need to meet with you and talk to you and see what you know, what you don't know. And based on this, I can give also kind of some points based on your actual performance and understanding of the subject. So the best way for me to do it, if after the exam, after the midterm, I'm gonna be meeting with each one and just go through the exam quick, 5 to 10 minutes max for each one. And if you like, you can ask your questions. Now, the way it works, you're gonna be doing this during the office hour and also maybe during the week. Some people are unavailable, they are not available at the office hour. So maybe we can do it after the course. If we have time, after the lecture, we can just stay, spend a little bit more time and discuss your exam if you want to. So if you like, you can wait till your discussion or review would come, and then we can talk about your question. Does it make sense?
Yeah. Okay. So what you say works. So I'll just wait till we meet and then try to ask it.
All right, very good. All right, you guys have a good night and go ahead and sign out.